Okay, today we're going to start into chapter P, and chapter P is preparation for calculus. The way this book works, the way it's organized, is Appendix C is pre-calculus. Pre-calculus you've already taken, so this is really a review that we did in Appendix C. Chapter P, this is where we're laying some of the groundwork down, and we're preparing for calculus. Preparation is really the stage. Some more work in areas you've already worked in before. And then we're going to move into a preview of calculus and finally do calculus. So we're inching our way towards calculus, and it's really the right way to go here so that we all have a firm foundation in all of these different mathematical areas before starting a brand new type of math. So today we're going to work with graphs and models. Now, if I asked you what a graph was, probably the first thing you would think of is a picture, is like a line or something, or a parabola, and that's a graph. Actually, that's not quite the case. A graph is defined as all of the solution points for a certain relationship between x and y, relationship being an equation, let's say. And the solution points can be represented a number of different ways: ordered pair, table, or you can draw it, and that would be called a plot. So that's an interesting thing to learn about the difference between what we think to be a graph and actually what a graph is. So a graph is actually the set of solution points for a relationship between x and y. Naturally, the relationship could be an equation. So the first relationship I've got here is an equation, y equals 2x plus 1. And I'd like to represent the graph of y equals 2x plus 1. It's a linear equation or a linear function, but I don't think we would know to even use that word if we didn't plot it, which, again, we normally think of as graphing it. But before we get to that plot, let's start by looking at the graph as a table, and we can do that. Now, if we were to graph as a table, we could set up a table of x's and y's, and x is independent. You can actually choose any x value you want and not necessarily be wrong. So I've chosen a bunch of different x values of interest: -1, 0, 1, 2, and of course I could choose some more. The y values are dependent. They depend on this equation, this relationship. So I went ahead and put a -1 in here and a calculated -1. I put a 0 into the equation and calculated a 1. I put a 1 into the equation and calculated a 3. And of course I put 2 in, and I got 2 times 2. 4 plus 1 is 5. So that is the graph of this equation. And normally you think of the graph as the actual plot or the line itself. And we can still refer to this as the graph because it fits the definition, which is the set of solution points. That is a set of solution points as a table. Another way to represent that is a set of ordered pairs. So ordered pairs, everything you need to know about ordered pairs is built right into the name because it needs to be in order, and the order is x and y. X comes first, and a pair, naturally, is a pair of numbers. So here is the graph as a set of solution points listed as ordered pairs: -1, -1, 0, 1, 1, 3, and 2, 5. And of course, I got that from the table up here, and you certainly know where the table came from. The table came from using the equation to make that calculation. So now what I want to do is I want to draw the graph as a plot. This is the traditional graph that you think of when somebody says, hey, can you graph that equation? You would think about the xy plane, the Cartesian plane. So let's go ahead and draw a y-axis, draw the x-axis, and label these. So if we label the x and y-axis, x would go here, y would go here, and we would mark off the integers: 1, 2, 3, 4, 5, etc. Over here, we'd mark off the integers: 1, 2, 3, 4, 5, etc. And then down here, -1, -2, -3, -4. And back here, -1, -2. let's label a few of these. Basically, it's two number lines, one vertical, one horizontal. So let's go ahead and plot these points, and therefore we can see the graph visually. First point is -1, -1. That would go about here. -1 for x, -1 for y. Second point is 0, 1. That would go here. Next point is 1, 3. 1, 3 goes right about there. And the last point we have, which is not the last point on the graph, it's just we only computed 4 points, is 2, 5. And 2, 5 goes about here. Let me just get it in the right spot there. Now, that's only 4 points. In order to visualize the graph, you want to see all the solution points. And look at that. They all line up because this is a linear equation. So it's a linear graph or a linear plot. So we put our arrows here to indicate that the graph, the plot, goes on forever and ever in both directions. So this would be the graph as a plot. Now, what's nice about having the graph as a plot, and I know that we just simply like to call this a graph, is that you can find new solution points without doing any math. In fact, if I reach in here and I place a point right here, make this one a little bigger than the others, I would probably identify that location if I come down to the x-axis as 1/2 for x, and come on over here to the y-axis, and it looks like it lands on the 2 for y. And that's a brand new ordered pair. It is a supposed solution point to the original equation, and we'll certainly test that. So this is the graph as a plot with all of the solution points on here. I'm going to label the ones that I originally put out there. This one right here is 1, 3. This one here is 0, 1. And over in the back here is -1, -1, right there. Now, I want to check that one, and I want to see if it's really correct. And the way to know that this point that we discovered is truly a solution point is to check it in the relationship. Y equals 2x plus 1. So in this case, x is 1/2, and y is 2, and it ought to make this relationship true. Let's find out. So 2 is my y. Is that truly equal to 2 times 1/2 plus 1? 2, is that really equal to 1 plus 1? And it is. So because the equation is certainly true for those particular x and y values, we consider it to be on the graph. It's on the plot, on the graph. It is an ordered pair, and we found it without using any math at all, really. We used the plot. Now, the next important thing to look at as we get further along is we've sketched a graph by plotting points, but what if I gave you an equation like this and you didn't know what the shape of that quadratic equation was? Now, many of you certainly do know, taking pre-calculus, that this ought to come out as the shape of a parabola. But without knowing that, I think we could just construct an XY table and watch that shape emerge just like we saw the line emerge. Again, you want to choose some interesting x values. It's up to you what you choose, but these certainly seem like reasonable x values to be working with. And the y values are not up to you. They're calculated. So let's go ahead and calculate our y values. -2 goes in. That would be -2 squared. That's 4 plus 1 is 5. -1 goes in. -1 squared, 1 plus 1 is 2. 1, and then 1 goes in. That's 2. 2 goes in. 4 plus 1 is 5. Well, there you go. You've got yourself the graph right there in tabular form. You could also list that out in as ordered pairs, and I'll do that for you here. -2, 5. -1, 2. 0, 1, 1, 2, and finally 2 comma 5. But the best way to represent a graph is a plot. And that's why we call the plot a graph most times. So once again, let's do this one last time, and that is just to plot some ordered pairs, and let's just see what the relationship is. The issue here is if you look at an equation, if you look at a table, if you look at ordered pairs, you really don't have a good feel for the relationship until you graph it by plotting it. And then all of a sudden you know, well, this is a parabola. It's very steep. Yeah, a small change in x gets you a big change in y. And it becomes very evident once we do that. So let's go ahead and put these here, and let's draw our plane again, xy plane. So I'll put my y-axis right here. I'll put my x-axis down here. And let's mark off a few x values. How about 1, 2, 3, and then back we'll do -1, -2, -3, and then up 1, 2, 3, 4, and 5, and down -1, -2 is probably enough. So let's label our x and y. And this is -1 and -2, and here's -1, -2, and -3. So let's go ahead and let's plot these. So first one I have is -2 comma 5. That would be here. -2 comma 5 is right there. Next one is -1 comma 2. That would be right here. Next one is 0 comma 1. That's here. 1 comma 2 is here. And 2 comma 5 is right here. Well, without really knowing the shape of this curve, it just sort of evolves on its own and emerges as a parabola. And you want to sketch this with a smooth curve. We don't want to connect the dots with lines. It's a smooth curve, so let it curl around here, and it comes up and then shoots off the page like that. So that's the idea. By actually computing some ordered pairs, you can draw the plot, and then you know exactly what you have. And you know what kind of shape it is. That's certainly not a linear equation, not a linear relationship. We actually refer to it as a quadratic relationship that yields this particular shape. The shape is called a parabola, right? Okay. Now, what are some of the interesting aspects of plotting a curve? Certainly the shape and how steep it is, but one of the useful components of the curve that might help you plot it would be the intercepts, and that's where the curve touches either the x or y axis. So let's talk about the intercepts. So this would be the x and y intercepts. Two different things. Now, if I were to draw you an xy plane like this, the x and y intercepts, well, let's start with the x-intercepts. The x-intercepts are where the curve touches the x-axis. It could touch here, maybe there, here. I'm not sure yet until I give you the relationship. But any of these points that I'm pointing to all would be x-intercepts if that's indeed where the curve actually touched. Now, all of these points share something in common. Think about what they share in common. Think about their y value. So if you think about it, the y value on all of those points is 0. So what you can do is feed the equation that information. You can say, I know that if it's an x-intercept, y value is 0, set y equal to 0, and out come the x-intercepts. Now the same holds true for the y-intercepts. See all these points? They're all candidates to be y-intercepts. Every single one of them. They all share something in common. They all share the x value to be equal to 0. So again, I'm not sure which of these should be a y-intercept. Not yet anyway. But what I can do is tell the equation that I know that x equals 0 because you're on the y-axis. Set x equal to 0, out come the y-intercept. So let's summarize that. So I want you to set y equal to 0 and solve for the x-intercepts. That's how you do it. For the y-intercepts, I want you to set x equal to 0 and solve for the y-intercepts. So let me give you a nice concrete example of how to find the intercepts. Let's use this equation right here. Y equals x squared minus 2x minus 3. Now, you're probably looking at that thinking that you would know the shape already because of x squared. It tells you that it's a parabola. In fact, if you look at the coefficient in front of the x squared, it's telling you specifically that it's a parabola that turns upward. So it's got to be a parabola. But the question is, where does it touch the x and y axis? In fact, be careful, because there may be a parabola out there that never touches the x-axis. That particular parabola says, I've got a y-intercept, but I have no x-intercept. So I'm not sure where this one touches the y-axis, and I'm not even sure if it touches the x-axis yet. So let's talk about finding the intercepts. So let's start with the y-intercept. So let's find the y-intercept for this one. And the way we're going to do that is by setting x to 0. So we get y equals 0 squared minus 2 times 0 minus 3. We get y equals, well, minus 3. And there it is, your y-intercept. So finding the y-intercept actually is not very difficult. In fact, the y-intercept is typically the constant hanging at the back of your function there, minus 3. So let's go ahead and plot minus 3 up there as a y-intercept. So I'm going to come down -1, -2, -3, and right there is my point. That's my y-intercept. So it's 0, -3, and I can call that a y-intercept. Let's go ahead and find some x-intercepts. And the way to do that is set y to 0. So let's find potential x-intercepts, possibly plural. Now, generally, if you have a function, you will only have one y-intercept. Think about why that might be. Think about the vertical line test, for example. Vertical line test, the y-axis is a vertical line. So therefore, the curve is only allowed to touch that vertical line once, and that would be your y-intercept. If it touches the y-axis twice, it fails the vertical line test, and it's no longer a function. It can, however, touch the x-axis more than once. So we put a plural here just in case. But to do this, we set y equal to 0. And so therefore, our function, which is hiding up here, we're going to select this y to be 0. So it will now say 0 equals x squared minus 2x minus 3. And I hope you remember how to solve these, right? Think about it. That's a quadratic equation. There's many ways to solve a quadratic equation. There are many ways. One is factoring. The other is the quadratic formula, completing the square. This one is factorable. Once you've found the set of factors that make up that quadratic, you can just set each factor to 0. And now we're going to get our two x-intercepts from here and there. So here we go. X equals 3 is an x-intercept. X equals minus 1 is an x-intercept. In fact, as ordered pairs, you just found 3, but remember we set y to be 0. You just found minus 1, and remember we set y to be 0. So let's go ahead and locate 3 and minus 1. Let's mark some more of these off here. So this is going to be 1, 2, say 3, and that should be an x-intercept right there. Now I'm going to come back here and make this minus 1 and minus 2 and minus 3. But of course, this also is supposed to be an x-intercept. Now be careful. The temptation is to just go ahead and start drawing the curve. But if you do, you're going to get a very lopsided parabola. So the reality is, I think if you're going to graph a parabola, the intercepts aren't enough. You probably want to look out for that vertex. And the vertex is the very bottom, in this case, of the parabola. So let's locate the vertex. And the vertex will be right between these two x-intercepts. So I'm going to march in 1, 2 units here. I'm going to march in 1, 2 units there. And so everything seems to point at 1. So I know now that my vertex lives at 1. I just don't seem to know the y value. That's what this is for. Okay, y values are pretty easy. Feed the x into the function, and it will tell you the y value. So let's see what the y value would be. Let's put the 1 in here. You get 1. You get 1 minus 2 minus 3. So I'm getting 1 minus 5. I'm getting a minus 4. So let's go ahead and plot one more point. It is not an intercept. It is the vertex that lives right here. So that's the y-intercept. These are x-intercepts, one here and one over here. And this is a special point we call the vertex. And let me label these as minus 1, minus 2, minus 3, and minus 4. One other thing, by the way, there is such a thing as the axis of symmetry, which is like a reflecting mirror. And you notice that this point reflects 2 units over and then across the mirror. This point sitting on the mirror, this point must reflect 1 unit over and have a companion reflection point right over there. So now you could sketch that parabola and know that this is a quadratic function. Think about what we did. We just found intercepts, and yes, we did find the vertex. That was very helpful as well. So there's a nice parabola with its intercepts and its vertex. So the intercepts are definitely important. Now, it's nice to talk about symmetry since we just brought up the parabola, because it does have symmetry. It doesn't have y or x-axis symmetry, but it does have symmetry. And in fact, it has symmetry about this dotted line, which is the axis of symmetry. In this case, that would be right here at x equals 1. Now, let's take a look at something here. There are other types of symmetry worth discussing, and that is x-axis symmetry, y-axis symmetry, and origin symmetry. Let's start with x-axis symmetry. Guys, if you have x-axis symmetry, this is what you got. You've got some kind of curve that lives up here, and the x-axis works just like a mirror, and you get a mirror image right down below it. And that's to say that if there were a point x comma y on your curve, there must also be a point x comma minus y on your curve. Now, how would you think you could determine if your equation had x-axis symmetry? Well, if you replace y with minus y, and you get the same equation back, you've got x-axis symmetry. So that's the test. And we'll definitely look at some of these equations to see that test in play. The other axis that we look at is the y-axis. Y-axis symmetry, okay? Now, let's go back to this one for a second, because this fails the vertical line test, so this is not even a function. Just keep that in mind. All right, let's look at y-axis symmetry. That is when the y-axis acts as a mirror. We can go back to one of the functions we used earlier, x squared plus 1, because that curve had something over here, but it had a mirror image over here. And again, that's to say that if there was a point on the curve x comma y, there must also be a companion point, a reflection point, which is minus x comma y. So that implies a nice test. And the test would be to replace x with negative x and see if you get the same equation back. And we'll certainly take a look at some examples of that. This is a function that passes the vertical line test. One more type of symmetry, which is referred to as origin symmetry. And origin symmetry looks like this. If you were to have a curve that has origin symmetry, it kind of looks like this. What's happening is this curve is reflecting down here and then reflecting across there. It's almost like you fold the paper into fourths. You fold it down and then over, and it overlaps each other. This curve here would have the point x comma y, and in fact the reflection is right through the origin, and you land on the reflected point, which is minus x and minus y. That implies a good test. And the test is to replace x with minus x and y with minus y, and then get the same equation back. So let's take a look at a couple of functions and see if they possess these kinds of symmetry. The first one I want to test is y equals x squared plus 1. I think that one has y-axis symmetry. It is a function, and I do think it has this kind of symmetry. In fact, that looks like its graph. So let's try replacing x with minus x and see what happens. So I'm going to take this and replace x with minus x. So it looks like this. Now you want to square the entire minus x. You need the protection of parentheses. But you know what? A negative squared is positive. So I'm getting y equals positive x squared plus 1. And that would be a big check mark. Y-axis symmetry. So we did get y-axis symmetry on that one. Let's try another one. Let's try x squared. Nope, not that one. Let's try y squared minus 1 equals x, something like that. Now, if you've played around with equations enough, you know that's not a function. Y squared is usually a giveaway that it's not a function. But is it x-axis symmetric? I'm going to replace y with minus y, and let's see what happens. So instead of y squared, you get minus y squared. In fact, negative squared is positive. And that's a big check mark. So we do have x-axis symmetry here. And if we were to graph that, you would see that reflection across the x-axis. One more, guys. Let's try this one. Y equals x cubed. Now remember, you got to do both tests if you want to test for origin symmetry. I'm going to replace x with minus x, and I'm going to replace y with minus y, and let's just observe. So minus y goes in here instead, and I get minus y. Minus x goes in here instead. We have to cube it, so we get minus x, but minus y is not going anywhere. 3 negative signs multiply out to be a negative. So we didn't get the same thing back, but all you got to do is divide both sides by minus 1. And look where we are. That would be a big check mark. So this one has origin symmetry, no doubt. That one has origin symmetry. Okay. The last thing we're going to do here, and by the way, you can use symmetry to certainly help you with your graphs, because if you know your intercepts, you just plot those. If you know your symmetry, boy, if you get a couple of points, you can reflect them across either the x, y, or the origin and get extra points that you don't even have to calculate. So they really do help plotting. The last thing I want to talk about is finding points of intersection. We'll finish this video off with that. So points of intersection. Let's say I had two curves, and these curves somehow touched each other. They ran into each other somewhere, but we're not sure where. So the first curve is, how about x squared plus y equals 2? And the other curve is going to be x plus y equals 2. Now, right off the bat, I think you can all recognize that these curves touch each other at 1, 1. Take a look at the equations. At 1, 1, 1 plus 1 is 2. That's a solution point. At 1, 1, 1 plus 1 is 2. That's a solution point. But is that the only point where these two curves intersect? So let's go ahead and see if we can figure out how to do that. First of all, let's try graphing these. If I subtract x squared from here, what I get is y equals minus x squared plus 2. If I subtract x, I get y equals minus x plus 2. I like these a lot better. They're a little easier to plot. So let's create a few ordered pairs by using a table. Negative, let's see, negative 1, 0, 1, 2, maybe even 3. Over here, more xy, negative 1, 0, 1, 2, and 3. Each one, the y values are computed independently of each other. They are dependent variables, though. These are the independent variables. Let's plug this in. Negative 1 squared is 1. Negative 1 plus 2 is going to be 1. 0, that's 2. I get another 1 here. Now I put 2 in, and I get 2 minus 4 is negative. Let's see, 2 squared is 4. So we get negative 2. And put 3 in, and you get 2 minus 9, which is minus 7. So there's some points on that graph. Over here, negative 1 is 1 plus 2 is 3, 2, 1, 0, and negative 1. That's very linear over there. Right away, you can see there's a solution point that's matching up 1, 1, but maybe we can find some more. Maybe we can find some more. Once again, here's my x and y axis. Definitely need to put some numbers here on the x-axis and also on the y-axis. And really, if you're going to do this graphically, the best way to do it is to use graph paper. We're just roughly putting this out here. So negative 1, 1 is my first point. Negative 1, 1 is here. 0, 2, 0, 2 is here. 1, 1 is right here. 1, 1. 2, negative 2 is, let's see, 1, 2, negative 2, that's here. And 3, negative 7, wow. That's way down here. Okay, let's see. 1, 2, 3, 4, 5, 6, and 7. We ought to be way, way down here. So I'm going to place a point here. What we've got here, guys, is a parabola. In fact, it's a parabola with y-axis symmetry. That means that there should be a reflection across the y-axis, and I see one right away from here to here. But why not reflect this point over? Save yourself the computation. So 1, 2 units over, 1, 2 units, place a point. This one's 3 units over, 1, 2, 3 units over, 1, 2, 3 units over. Place another point and see that parabola resolve itself quite nicely. So we're going to sketch the parabola in here so you can see all the solution points sketched in. It is an upside down parabola, and it comes through here and shoots off the page in that direction. Now the next thing we're graphing is this line, and there's many ways to graph a line with point and slope. Intercept and slope, but why not use these ordered pairs that we just discovered? Negative 1, 3. 1, 2, 3, negative 1 goes there. 0, 2. 0, 2 is right there. It's another intersection point. 1, 1 is here. 2, 0 is here. 3, negative 1 is over there. So here's that line, and it's not a tangent line, actually, because the line actually goes through the parabola like this. So there's actually two intersections. There's one here and one here. We already knew about this one, but maybe we didn't know about that one. So things lined up really well on the graph. Let me show you how to do that algebraically. One thing for sure, when we intersect two curves together, you notice that the x and the y values of the solution points are the same. Specifically, the y values are the same. This has a y value of 1, and this also has a y value of 1 from the curve. So what we do with equations here, we take our y equals minus x squared plus 2, we take our y equals minus x plus 2, and we say we want to know when the y values are equal to each other. So what do? Well, this is a representation of the y value. This is a representation of the y value on that curve, and we simply do that. We set them equal to each other. And watch what happens. This is a quadratic equation. Let's move everything to one side by adding x squared and subtracting 2. By adding x squared and subtracting 2. You get 0, because that's what you need to do for a quadratic equation. We have x squared minus x plus 0. How do you solve this quadratic equation? By factoring. Now this one's easy because it's just a common factor. What do we do next? We set each factor to 0. So where do these two curves intersect? At x equals 0 and also at x equals 1, which is, of course, what we learned from the graph. But what about the y values? Well, the y values are supposed to match, so actually, I don't care which function you use. They both better give the same y value. So for x equals 0, we get y equals 2, or we get y equals 2. So the intersection point is 0, 2. For x equals 1, if you plug that in over here, you get y equals 2 minus 1 is 1. And if you put it in here, 2 minus 1 is 1. So you can use both of them just to check, but they better be the same. And there they are. Intersection points. Okay, so we finished up with chapter P1. It's a lot about graphing, plotting, it's finding solution points, looking at the graph, visualizing the graph. If you read that last page, page 7, you'll see that we use these graphs to model things. And I'd like you to read page 7 so you know why we have these equations, why we use these different graphs, because we don't do it just for math's sake. We model things. Maybe temperature increases and the chemical reaction increases with temperature in a linear fashion. We would use a linear model. We would use a line or a linear equation. Maybe it's the other way around. Maybe instead of being linear, it's quadratic. Maybe you increase temperature a little bit and the reaction goes way up. And maybe the reaction peaks, and then if you put too much temperature in, the reaction goes down. Well, you need yourself a quadratic model for that. So take a look at page 7 to see how we fit a mathematical model to data that we see. So we'll see you in the next video. Thanks very much.